In today's basic organic chemistry class, we are going to look at hydrocarbons. At the end of this class, you understand what hydrocarbons are, with emphasis on alkyl halides. You will understand the nomenclature, that is naming, isomerism, physical properties, their method of preparation, and their chemical reactions. Simply put, hydrocarbons are organic compounds that are obtained from hydrocarbons. Hydrocarbons are compounds that contain just hydrogen and carbon. They are the alkanes, the alkenes, the alkynes, and the aromatics. Aromatics are benzene family. This is obtained by simply replacing one or more hydrogen atoms of these hydrocarbons with halogens. The halogens are the fluorine, chlorine, bromine, and iodine. This will give rise to 4 types of hydrocarbons, which are alkyl halide, haloalkanes, haloalkynes, and aryl halide or halobenzene. Alkyl halides. These are obtained by replacing one hydrogen of alkane with halogen. Remember, the carbon in alkanes are sp3 hybridized carbons. So the carbon of alkyl halides are still sp3 hybridized because the presence of the halogen did not affect the saturation. So when alkane loses one hydrogen, it becomes alkyl. So this hydrogen that is lost is coming back as halogen, forming alkyl halides. Haloalkanes or alkyl halides are simply formed by replacing one hydrogen of alkanes with halogens. These are called vinyl halides because alkanes are sp2 hybridized. Vinyl halides are also sp2 hybridized. But there are some haloalkanes that the halogens are not directly attached to sp2 carbon. sp2 carbon is carbon that is bearing the double bond. A typical example is the alkyl halides, where the halogen is at the terminal carbon that is saturated. In that case, the carbon bearing the halogen is sp3 hybridized carbon, but the compound still remain sp2 hybridized. Next is haloalkynes. In the same manner, haloalkynes are sp2 hybridized carbon. So when one of these hydrogen is replaced with halogen, it becomes haloalkyne, and they still remain sp hybridized. Halobenzene or aryl halides are formed by replacing one hydrogen or more hydrogen in benzene with halogen. The halogen is directly attached to benzene ring. We also have benzyl halide. In that case, the halogen is not connected directly to benzene, but to the carbon connected to benzene. When you have toluene, toluene is when I have methyl carbon connected to benzene. So when one hydrogen of this methyl is replaced with halogen, we call it benzyl halide. Remember, when this halogen leaves, we have benzyl carbocation. This benzyl halide behaves chemically like alkyl halide because the carbon on that halide is sp3 hybridized, while the carbon in benzyl halide as a compound is sp2 because benzene is sp2 hybridized compound. This alkyl halide, which is emphasis we are going to depend so much on, is classified into three: primary, secondary, and tertiary, just like the way alcohols are classified. How do I know primary, secondary, and tertiary? Look at the carbon that bears a functional group. What is a functional group? A functional group is that atom or group of atoms that defines a compound. In that case, what defines this halide is the halogen. So halogen is a functional group in alkyl halide. So the carbon that bears this halide is going to determine whether the alkyl halide is primary, secondary, or tertiary. When that carbon is having two hydrogen, we are going to call that alkyl halide primary alkyl halide. When it has one hydrogen, becomes secondary. Remember, secondary is always called iso. When it's tertiary, the carbon bearing the halogen will have no hydrogen. So that's the same thing, any primary, secondary, and tertiary that has to do with organic compounds. In naming, IUPAC system is being employed. When naming, the method of naming normal hydrocarbon is being employed here. But the difference is that the position of this halogen will be indicated, and halogen will be given priority besides unsaturation for alkyl, haloalkanes, and alkenyls. But for haloalkanes, the priority will be given to halogen because there is no double bond in haloalkanes. Example, the one we have is methyl bromide, can also be called bromomethane. Ethyl chloride can also be called chloroethane. Looking at the other compound, you realize that the carbon that is bearing the fluorine is having one hydrogen, so it is secondary alkyl halide. In that case, every secondary is called iso, so that's why it's called isopropyl fluoride or 2-fluoropropane. The last compound is tertiary compound because the carbon that bears the halogen does not have any hydrogen. It has methyl all, so that's why we call it tertiary. Why is it tertiary butyl? Because the carbon is 4 and it is tertiary, so we call it tertiary butyl iodide or 2-iodo 2-methyl propane. When naming aryl halide or the halobenzene, you have to indicate the position of this halogen in benzene ring. The first compound is only one halogen and there is no other substituent, so we call bromobenzene. The second compound have methyl. Now in exam, if you have an option that call this methyl and benzene toluene, is much more appropriate. So but in this case we are using 2-chloromethyl benzene. It can also be 2-chlorotoluene. When we are having more than one substituent, remember alphabetical order is supposed to be considered. That's why we have 2,4-dichloro nitrobenzene, because chloro comes before nitro. The same thing applies in every naming. Alphabetical order must be maintained. And whenever you're naming, number and letter is separated by hyphen. Number and number is separated by comma. Isomerism is a phenomenon whereby two or more compounds have the same molecular formula but different structural formula, just like twins. So if you see twins, they have the same date of birth, but something must differ among them if there are 3, or between them if there are 2. Either one is fat, one is tall, one is slim. So that's isomer. So in alkyl halide, isomerism starts from propane. So in propane, you have 2 alkyl halides, which means 2 isomers. Butane is going to have 4 isomers. So these isomers can either be position isomers or chain isomers. So we're going to have positional isomerism or chain isomerism when you come to alkyl halides. In this example, we are using this compound to show the position isomers. In that case, the first compound is 1-chlorobutane, making it a primary because the carbon that is bearing the halide is having 2 hydrogen. The second compound is 2-chloro, making it a secondary alkyl halide because the carbon bearing the halogen is having 1 hydrogen. The last one is tertiary because the carbon bearing the halogen has no hydrogen. So that's why they call it position isomers. In chain isomerism, we are moving from straight chain to branching isomer. So from 1-chlorobutane to 1-chloro-2-methylpropane. These are called chain isomers. Physical properties of alkyl halide. Alkyl halide exhibits higher boiling points than corresponding alkanes. When you talk about corresponding, it means comparing with alkanes of the same molecular weight. And the reason is because the carbon halogen makes alkyl halide polar. But the polarity is that which promotes dipole-dipole interaction in liquid phase. Because it cannot undergo hydrogen bonding with water, it is not soluble in water. So the boiling point of this alkyl halide will increase with the atomic mass of the halogen. So meaning that the higher the atomic mass, the higher the boiling point. Comparing, the boiling point of methane is -162, while that of methyl chloride is -24. So between methane and methyl chloride, difference is the chlorine. Now, between -24 to methyl bromide, +5, meaning there is increase in molecular weight from chlorine to bromine, causing increase in boiling point. When it gets to iodine, the boiling point increases more, validating that the higher the molecular weight of the halogen, the higher the boiling point of alkyl halides. Hydrocarbons are generally not soluble in water, but they are soluble in organic solvent like ethanol. The reason is because despite that these alkyl halides are polar, they cannot form hydrogen bonding with water. Alkyl halides are generally denser than water because remember the weight of the halide makes them denser than water. The alkyl halide of methane are gases. Other than methane are volatile liquids, and most of them exhibit sweet smell. It doesn't make them to be aromatic, and it doesn't make them to be esters. How are these haloalkanes or alkyl halides prepared? They can be prepared by halogenation of alkanes, halogenation of alkanes or alkynes, by hydrohalogenation of alkanes, and by substitution reaction in alcohol, which can be done by using halogen acids or phosphorus halides or thionyl chloride. When talking about halogenation of alkanes, this happens using free radical mechanism. In this method is very useful only in industry. The laboratory usage is very little. This happens in the presence of UV light or high temperature. When the hydrogen in alkane is being replaced, substituted with halogen. So it will continue until all the hydrogens are replaced with halogen. That's why at the end we're going to form tetrachloromethane, which means all the hydrogen in methane has been replaced with chlorine. It follows 3 steps in mechanism: propagation and termination. Initiation stage is where these radicals are being generated. Remember, because chlorine molecule are symmetrical in the sense that the electron cloud are symmetrically disposed. So when they are divided, they are going to be divided homolytically to form radical. So this radical is going to react with alkane molecule. In this case, we are using methane as a case study. So we're in propagation stage, radical reacts with molecule to form radical and molecule. So whenever you're doing propagation, you must start with radical and molecule and end with radical and molecule. So when you want to terminate the reaction, you go to termination step. In termination step, you're using 2 radicals to form molecule. If there is no molecule in the compound, if I see any evidence of radical, the reaction is in propagation stage. Until it's terminated, it continues. So that is why it is a reaction that continues until all the hydrogen has been replaced, except you intentionally terminate it. Alkanes or alkynes can also be halogenated. When halogenation of alkane, you need 1 mole of halogen, and the halide formed here is going to be dihaloalkanes. But when you want to halogenate alkynes, 2 molecules of halogens will be needed, because you're going to form 2,2,3,3 tetrahaloalkanes. When preparing alkyl halide using hydrohalogenation of alkanes, Markovnikov's rule will be employed only if the alkene in question is not symmetrical. Remember, symmetrical is what can be divided into 2 equal halves. So when the alkene is asymmetrical, I can use Markovnikov's. But the example we are having here is symmetrical. So in symmetrical alkene, Markovnikov's rule is not needed. It means I can fix my hydrogen or halide however I want it. But if it's asymmetrical, I will follow Markovnikov's rule. What does Markovnikov's rule say? The rule says that when I have a double bond, a compound that has double bond, and I have hydrogen halide that I want to add to this compound, the carbon that bears more hydrogen will be given hydrogen. The carbon that have less hydrogen will be given halide. Assuming I have water and I want to add it across the double bond. Remember, water can split into hydrogen and hydroxyl. So the carbon that have more hydrogen is going to get the hydrogen. The carbon that have less hydrogen is going to get the hydroxyl. So that is how Markovnikov rule is being employed in unsaturated system of alkane. The next method is by substitution reaction in alcohol. In this reaction, the hydroxyl, which is a nucleophile, is going to be replaced with halogen, which also is a nucleophile. First method is using Lucas reagent. Lucas reagent is hydrogen chloride in conc hydrogen chloride in conc zinc chloride. The zinc chloride is acting as a catalyst, which is a dehydrating agent. In that case, the hydroxyl nucleophile will be replaced with halide to form alkyl halide, and water will be taken away by zinc chloride, which is a dehydrating agent. Now, this particular method is used to distinguish between classes of alcohol in the lab. When Lucas reagent is added in tertiary alcohol, there is instant reaction. When added to secondary, reaction occurs within 5 minutes. But when added to primary, the reaction is irresponsive. Even at times when heat is added, it might not be responsive. So with this, you can distinguish between classes of alcohol. Remember, in Lucas reagent, zinc chloride is a catalyst, which is a dehydrating agent. There is limitation of Lucas reagent in preparation of alkyl halide because there is rearrangement of alkyl halide, which means that the starting materials is going to be different from the product we are going to obtain. This rearrangement limits applicability of Lucas reagent in preparation of alkyl halide. Next is preparing alkyl halide from alcohol using acids. These acids will be phosphorus halides, which can be phosphorus trichloride, phosphorus pentachloride, phosphorus tribromide, phosphorus pentabromide, phosphorus triiodide, phosphorus pentaiodide, or thionyl chloride. In all these reagents, what happens is still the same thing, where we are going to exchange the hydrogen nucleophile with halide nucleophile. Now, if the product I'm expecting is alkyl bromide or bromoalkane, then the reagent I'm going to use is going to be phosphorus penta or phosphorus tribromide. So what I'm forming will determine the phosphorus halide I'm going to employ. But in all, thionyl chloride is the best method of preparing alkyl halide from alcohol. The reason is because if you look at the byproduct, thionyl chloride have gases, and these gases removed using pyridine. So because pyridine is going to remove these gases formed, alkyl halide obtained using thionyl is going to come in its very pure form. So that is why thionyl is the best method of preparing alkyl halide. This method is better, has advantage over the one of Lucas reagent. Despite coming up in its pure form, there is no problem of rearrangement of the alkyl. So it is a better method than Lucas method. In preparation of halobenzene or aryl halide, we are going to talk about direct halogenation of benzene. In this direct halogenation, the catalyst you're going to employ will be determined by the halogenation you are interested in. If you're interested in bromination, you would going to use bromine molecule with bromine catalyst. The catalyst is ion 3 halide. So if it's bromine, it's going to be ion 3 bromide. If I want to chlorinate, my reagent will be chlorine molecule with ion 3 chloride. So that is how to obtain benzyl. That is how to obtain halobenzene. The reactions of alkyl halides. We are going to look at reactions that are called nucleophilic substitution reaction, where we are going to substitute a nucleophile with the alkyl halide. Remember, the nucleophile can be hydroxyl, alkoxide, cyanide, carboxylate, ammonia, or alkanide. Now, what is happening here is that halide, which is halogen, is going to be replaced with each of these nucleophile. What is a nucleophile? A nucleophile is a neutral species, example water and ammonia, that have lone pair or unshared pair of electrons. A nucleophile can also be a negatively charged species like hydroxyl or cyanide that have that negative sign there, makes it a nucleophile. It's confirming that it has dense of electron. It is wealthy of electron. Wealthy of electron makes it easier for it to donate electron. Lone pair of electron means there's electron not usable, so it can be released. Just like you have things you don't use, it's easier for you to give it out. So that's what is a nucleophile. Or a man that has excess money can easily give out money. That is a nucleophile. They are enriched with electron. And that's why they are always attacking a center that is deficient of electrons, which is designated with positive center. So when positive meets with negative, they are going to form a bond, and that is how new bond is formed. So example of the reactions are as shown on the slide. You realize in this reaction, the halide is being replaced by nucleophile. A typical example of this reaction is formation of ether. The first we are going to look at is hydrolysis of alkyl halide. When alkyl halide are hydrolyzed, we are going to form alcohol. Remember, from the first time, alcohol was a method of preparing alkyl halide by substituting the hydroxy group in alcohol with halide. So in the reaction, we are reversing the process. So in this case, we are going to use alkali, which can be sodium hydroxide or potassium hydroxide. Moist silver oxide can also be used. What happens is that our interest is not in the metal but in the hydroxy group to exchange it with our halide. So we're going to form alcohol. When elimination reaction want to be limited, we use moist silver oxide. The next reaction, like said, was formation of ether. In that case, the alkyl halide is going to react with alkoxide, either sodium alkoxide or potassium alkoxide. It can also be sodium phenoxide. In that case, this metal is going to form bonding with the halide. Then the oxide is going to form bonding to form ether with the alkyl. So that's the same thing that happened with phenoxide. This method is used in preparing ether. Method is also known as Williamson ether synthesis. In Williamson ether synthesis, only primary alkyl halide or methyl alkyl halide are useful. Secondary are problematic and tertiary are never possible. If you look at the reaction, you will understand that the bromine is a good leaving group, so bromine is going to leave and bond with sodium to form sodium bromide. Then that space bromine leave is going to be positive, while sodium metal is going to leave a negative center on oxygen because oxygen is highly electronegative, so they are going to form a bond, forming an ether. The same thing happens when you are using sodium phenoxide as your alkoxide. This is Williamson ether synthesis. Don't forget, it's only primary alkyl halide or methyl that is useful for Williamson ether synthesis. reaction is a reaction of carboxylate ion. When reacted, esters are formed. In that case, the silver salt of alkanoic acid is going to react with alkyl halide. Then that silver metal is going to form bonding with bromine to form silver bromide. Then the ester, remember in ester we have carboxylate end and alkyl end. This alkyl end is not coming from alcohol, it's coming from alkyl halide. So that's why we're going to have ethyl ethanoate, because the acid is ethanoic acid. So we're going to have ethyl ethanoate as our ester. Come to the end of this first section of our alkyl halide. You can also go back and go through it over and over again. Remember, the essence of making it a recorded class is for you to listen to it even when you're on the wheel, when you are in the place where your place is noisy. You can use your earpiece to listen. The more you listen to this, the more they become part of you. So when you enter exam hall, just the way you read songs, you sing songs without reading the lyrics, things will be flowing and the exam will be very simple for you. I wish you success in your journey in 213. I will see you in the next class where we're going to finish this topic of alkyl halide. Thank you.